let's get started. Cool beans. All right, here we go. So, TCP/IP Illustrated Volume 1, talking about the protocols, the second edition by Kevin R. Fall with Richard Stevens. Interesting. Cool. So this is obviously split into two photos. So from your modem, you should get given a list of IP addresses, right? So you have a list of IP addresses which are attained from your ISP, right? And from here, your router will dictate a lot what everything gets assigned to, and each device has a local MAC address. Local MAC address, which obviously gets assigned, right? And then you can have a switch, which then parses out these more, so you're able to split up, obviously, and have more devices per thing. And actually what I might do, because I'm looking down a lot, I might move my camera to the bottom. Let's do that. So we can drop this down without breaking anything. Cool. Let's see how this looks. So if I'm looking down like this, technically, if I do something like this, yeah, that's a lot better. If we move the camera down, cool. All right, let's get started. So this is what we have, right? So we've got local MAC address, we've got a router, which gives us a list of public IP addresses, right? Linked to your internet connection to your internet service provider, right? And it looks from here, the switch starts, they all start with the same IP address, and then obviously the last one dictates the specific devices. Same thing with an access point here, gets derived one as well. And then you have dynamic IP addresses for obviously your router, your Wi-Fi box, right? Your access point. Obviously you go Ethernet, you can go straight to your device, or you can also plug your Ethernet through your access point, and your access point will define what the local MAC address and IP address is when it shoots back out, which is cool. This is obviously a log for myself, so I can look back and see how much I've done, but I know a lot of this already from university, so a lot of this will just be review. I won't be doing too much exercises or notes because I've done this before, right? So let's look into this. So all of this connects out to your modem. Your modem shoots out to the internet with a bunch of these DNS servers, which then can dictate where messages passes through, right? And then you have the same thing here for a coffee house. It's got the same idea. And for an enterprise system, they've got something similar as well, right? And they'll have something that looks like this, right? Got a router, and then they have these networks which then can pass to other devices, and I'm assuming the same as well. But I don't know about DMZ networks, but we'll learn about them a bit more, which is cool. So this is more about praise, about the first edition, the Bible for TCP/IP developers. It's quite funny. Showing how great the book is. It's awesome. It gave enough background and commentary for the novice. Much better than theory. They actually show stuff, make it readable and informative. Cool. TCP/IP Illustrated Volume 1, the second edition. Cool. Nice little forethought here, and a thank you for the insight knowledge to these people. Cool, so let's get into this a little bit, right? forward preface. So let's just have a look at, so what I'm going to do now is actually have a read of all the chapters from a broad perspective to actually see what we're going to go into, right? So there's quite a lot here. So we jump back up to the front. Architectural principles, packets, connections, data ground, fate sharing, arbitral flow. Something I should probably take a look at as well is I actually have in photo that I'm going to pull up, which covers if I need to skip any sections that aren't necessarily apparent, because it can sometimes make things TCP/IP. I'll read the whole thing, it appears. Oh, actually we can parse and have a look right here. So the chapters I should read is 1 to 4, 1 to 1.4, 2 to 2.6, 3 to 3.4. Cool, so I'm just going to read these chapters and stay online so you know what to keep track of. So today we'll try to read 1 to 1.4, and 1 to 1.4 is the architectural principles, design implementation, architecture protocols, TCP/IP suite, and intranets and extranets. If I had infinite time, I'd read the whole thing, but we don't, right? So I will come back and read the stuff we don't need to read, but what we need to read is this one, 1 to 1.4, and 2 to 2.6. We'll try to get these done. And then we'll also cover today internet address architecture, expressing IP addresses, basic IP address structure, CIDR aggregation. Not sure what this is, right? This is something we'll have to investigate into. Special use addresses, allocation. I think that's it. And then 3 to 3.4. So we'll cover these on another lesson or another study session. So let's just do these for now. Yeah, and see how far we get. I've set an hour to study. Obviously some time is spent for planning, but we should be okay. So we jump back to the book. I'm going to keep a list on my screen so I can also see what I need to cover. So we'll cover all of them up to 1.4. Cool. All right, let's get started. Just to note, and for users who deal with TCP/IP applications on a daily basis, we all do if you use a computer, but also if you're a software engineer, this is probably vital, I think, which is, and users who deal with this on a daily basis. Just getting a phone call. I will be back. We're back. Just have to take a phone call, sort out some business. Cool. misses. Back to studying. Also, just to summarize, anyways, it just covered the reason that we had packets. So the data packet covers its endpoint, so it doesn't matter who it's routing through, it just routes to the thing that it needs to go to, which is pretty cool, right? It's pretty awesome. Instead of it having to update after every chain, it has a datagram and has message boundaries or record markers issued when an application sends more than one chunk of information. The fact that one more chunk was written may not preserve the communication protocol. So you just provide message boundaries. The application must provide its own. Application writes to network. Protocol preserves message boundaries. Application reads to network. 1, 2, 1, 3, 1. Application read function returns the same size as the corresponding writes. Application read function returns however much application requests. 6 reads are bytes each. Applications write messages that are carried in protocols. A message boundary offset by one write to the other. Protocols how the read functions. Application read functions return however much application requests. 6 reads, 6 are bytes each. I see. So you're grouping them by bounds, right? I mean, that makes sense, right? So you don't, you can preserve your messages so things don't get lost in translation, right? That makes sense. So this is the classic OSI model that we've all seen before. Um, it's quite interesting actually because you learn this all the time. To be honest, you don't really need to care as a developer until you get to the higher level. A lot of the network devices are handled by like a local IT person, which handles the physical networking of places. But to be quite frank, as an engineer, a lot of these are handled by like by a library, and the presentation and the application is kind of how you interface with code. It's from my general understanding for the most part. So we only really need to worry about layer 7 and 6. Maybe not even layer 6, to be honest. That's handled by a lot of the core libraries on your operating system. But I think, develop application develop. So it's really just the application layer we really need to care about in our case. But I suppose if I ever work on anything embedded, the rest of the layers are quite helpful, right? I feel like the hardware at some point, the physical, unless you're developing the onboard system yourself, physical, and then application layer. Even then, a lot of this is obfuscated from the board when it's developed, right? So, yeah, it's quite interesting. This is the classic model that everyone refers to. I mean, it is the standard, right? So, yeah. So from my understanding, a lot of what this is, which is when you use protocol multiplexing, you need to have some type of data that identifies where it is. So there's a packet called the protocol identifier field in each packet, which basically tells you what layer it's in. And there's multiple objects at layer n can be multiplexed together. So there's an identifier. When you get a packet come through and it's going through certain layers, you can group them depending on what it is, right? This is my understanding from what the protocol data unit PDU. The PDU has a protocol data unit has a protocol identifier within the packet to say if they're all in the link, and this comes from the physical layer, and it's like an n-1 or an n- I, where I is the current layer that you want, right? Which makes sense, right? You need a way to identify what information is part of what object, right, within the packet. Don't know what it looks like, but it makes sense that there's something there, right, which is always useful. So something like this actually is more what I was trying to draw out before. You have the hosts, right? So up here is how you actually interface, right, with sending packets. So you either interface between with HTTP or DNS or DHCP, right? Um, and this will then talk to a web server, or so I think it's deeper than that, right? Because then it talks with UDP or TCP, so that's actually what sends the request at the web server level, is my guess. So an HTTP has the packet, the header, and everything. Then that gets parsed down again, so that gets distilled down to TCP or UDP or SCTP or DCCP, which I have not obviously read yet. That's further down. And then once it goes through into the web, there's a bunch of stuff. There's the network adjunct layer and the network layer that does a bunch of stuff with IPs, right? With IPv6 and the type of 32-bit addresses and everything. And then you get down to the driver level, right? The link adjunct layer. And it uses to map addresses so it knows where to go. To be honest, as an engineer, software engineer, and hopefully to be a quant one day, I really do think we just need to sit up in the application and transport layer, because a lot of this is obfuscated for us by great IT people. Like all of this, I need to know it, but we don't necessarily care about it too much, right? Like I'd probably say like this is like not important, but this is quite important, right? Useful. Obviously, I'll eventually go through and read all of this, but the stuff I need to prioritize is stuff that'll help me as a software engineer and as a quant. So just figuring out types of protocols, right? So the type of application layer protocols and then type of transport layer protocols. A lot of this stuff here is defined by like the backend team when they're setting up something initially, right? And a lot of this is kind of, I mean, this is all backend if you think about it, but this is more like the server and how we set up the WebSocket and web server stuff. And this is more like the API that we use to inference or HTTP request, whatever. So yeah. The application layer and transport layer are more what we care about in this case, but all of it is obviously important, but we just care about the top two layers in the ARM TCA IP suite, pretty much. But yeah. And this actually answers my question. What's the difference between IPv4 and IPv6? I've just seen it in the tech we're looking at routers or anything, right? And the difference is the routing table. So you can store a lot more, or not the routing table, but the amount of data that you can hold within routing. IPv4 only has 32-bit addresses, so up to 64 kilobytes. In IPv6, you can hold up to 4 GB. You have 128-bit addresses. I'm assuming as the internet increases, right, with more people being connected, the packet, you can hold a lot more data in each packet. So you can have these massive packets passing through. I'm assuming it's higher data throughput overall, right? Because you can send more at one time, which is cool. Also, just something I didn't know, but I now know, is the packet that stores all the different layers of information is called an IP address, which is cool. So an IPv6 IP address can store a lot more, up to 4 gigabytes, obviously, per packet, and then IPv4 can only store 32-bit, which is like 64 kilobytes or something. So that is just called an IP address. And we have stuff called forwarding. So I've done stuff in the past when you're a kid and you set up a game server like 5-6 years ago, and you can port forward it. Essentially, you're just forwarding the IP address to the next router in the chain, right? Which is cool, right? The process of making this determination of where the datagram should be sent is called forwarding, and it's next hop, which is awesome. And routers tend to do this as well. So that's a little tidbit. So this is where we actually learn the difference between TCP and UDP, right? So TCP, you have a bunch of cool stuff like packet loss, duplication, reordering, which is like quite important, right? I think most of the web runs on TCP, but I wonder, it might be something to ask Claude or ChatGPT or just Google when you would use stuff for different occasions. Connection layer. Conversely, the UDP provides UDP is just a little bit more than IP. It allows applications to send datagrams and preserve message boundaries. So UDP preserves message boundaries, but there's no rate control or error control. So from my understanding, I'd assume because UDP is just a little bit more than IP, the actual packets would be smaller. And you can get them a lot faster and send a ton at a time. You send 10 UDP packets at one go, right? There's no error control. But the messages are preserved. But obviously you can just send a ton of packets in, so you probably don't want that for the internet, right? You can just spam people with packets. But yeah, and it does explain it on this hand here. This whole paragraph I should have just kept reading. But the thing is, I don't like to be told something and not question into it and not think about it. It's useful to think about things as well, right? I think the Primogen talks about that quite a lot, about being sent something. Or when you're... Primogen talks about when he reads an article, he likes to think about it and then continue reading, because it forces your problem-solving thinking mindset, right? You don't just consume data and think it's true. But obviously, I think it can't answer my own question reading the next block of stuff. I just realized I wasn't talking. Just did a review, learned what a packet is, learned what IP addresses are, understood the difference and benefits between TCP and UDP, which is cool. And there's another one called SCTP, which is a streaming one, which streams in data. All data streamed if you think about it. But I think it sets up a connection, but it hasn't gone into SCTP yet, but we know UDP and TCP, which is cool. So the transport, I don't actually know what they stand for. It's definitely somewhere. Yeah, SCTP is the Stream Control Transmission Protocol, and it does not require the sequencing of data to be strictly maintained, but it also allows multiple streams to be logically carried. Don't know how that works. It's kind of a mix between the both. And then you have UDP and TCP, which is cool. That's it for today. We also know what a packet is. It just provides where it needs to go for each of the layers, right? And yeah, look into port numbers as well. And then we also learned the difference between IPv4 and IPv6. IPv4 allows for 32 kilobytes of information, whereas IPv6 allows for 6 gigabytes. So the amount of packets you can send is greater, I think, and I could be wrong. And there's different types. There's IPv6, IPv4, and there's a thing called tunneling, which in the indicator for the next header you can do a thing called tunneling, which actually provides the data anagram. But I'll read what that is. It's a main downer if that's not an important chapter. But that's for today. We just did an hour of reading TCP IP Illustrated Volume 1, and we've actually just learned slightly about the protocols and what a data packet is and what an IP address is. That's it for today. And we've ended on page 56. And again, this is just a log for myself. So I know what I've read when I've stopped reading, what I've covered as well. TCP IP Illustrated Volume 1, page